Hello everyone, I am Sunanda. Let me tell you a little bit about who we are and what we do. Gudsky Research Foundation is an educational and research based organization that believes knowledge should never be limited by money. That's why we offer a 6-month free educational series on applied artificial intelligence and machine learning. Our aim is to help every student, no matter where they come from, understand complex AI topics in simple, practical ways. We break down through theories into easy to follow lessons, supported with examples, projects, and real world applications. And the best part, everything is absolutely free of cost. You don't need to pay for any module, any lecture, or any certification in this 6-month journey. We at Good Sky strongly believe in learning by doing, so each topic concept, theory to practice, the same way professionals apply A&ml in industry today. So now let's move into today's topic, one of the most important concepts in machine learning that affects every single model you train, that is the bias variance, trade-off and overfitting. So what we learned today is bias variance, trade-off. Okay, all right, before we jump deep, let's understand what this session is all about. Machine learning models are built to learn patterns from data and then make predictions on new unseen samples. But here is the catch, not all models behave the same way. Some models are too simple, they fail to learn enough from data. We call that underfitting. Others are too complex, they remember everything, even the noise, and that's called overfitting. Now, the bias variance trade off helps us understand this balance between a model being too simple and too complex. So, think of it like a tuning a guitar. If the strings are too loose, the sound is dull. That's underfitting. If they are too tight, it hurts. The sound it harsh or breaks. That's overfitting. But when tuned perfectly, you get beautiful music. That's the right balance, the perfect trade off. In the same way, the bias variance trade off helps us tune our ML models so that they can generalize well to new data instead of just memorizing the old one. So, this is what the bias variance trade off, and then this is why we are learning today about this bias variance trade off, and the concept directly connects with learning curves, regularization techniques, and model evaluation. Learning curves are usually for generalization, and regularization techniques is used to control the overfitting, and finally model evaluation is to find the good spot between the underfitting and overfitting. So now we move into the next slide that may be understand for you goodly. So why study bias and variance? So let's answer the big why. Why should we even bother learning bias and variance? So in machine learning, success isn't about how great your model performs on training data. It's about how well it generalizes to data it has never seen before. Okay, for example, imagine you built an AI to recognize cats and dogs. If it performs perfectly on the photos you trained it with, but fails when you give it new images, then what's the use? That means your model has overfitted. So here is a few key reasons why bias and variance matter. Okay, first, we see generalization goal. Our goal is not memorization. A good model must predict accurately on test data, not just on training data. And next one, understanding overfitting versus underfitting. Overfitting means low training error but high test error. Underfitting means high error on both. So, bias variance gives us a mathematical and conceptual way to understand this. And next, we go for trade off principle. When we reduce bias, variance often increases, and vice versa. Our job here is to find the correct spot a balanced model that performs well on both training and testing. And next, we see the model selection. Every ML algorithm, whether it's linear regression, decision trees, support vector machines, or neural networks, depends on this concept to adjust parameters, architecture depth, and regularization strength. So, in short, understanding bias and variance is like learning the DNA of every machine learning model. Okay, and next, model generalization concept. Now that we know why bias and variance matter, let's understand generalization, one of the most powerful ideas in ML. Generalization is simply a model's ability to perform well on new data that wasn't used in training. So let's this relate to a real life. Imagine you are learning how to drive. If you only practice on empty roads, you will do well there. That's like your training data. But when you go into real city traffic, the test data, will you still drive well? If yes, that means you have generalized your learning. If you panic and make mistakes, you are overfitted to easy roads. So, in technical terms, training error means the error your model makes on the data it already saw. And the test error means the error it makes on new unseen data. The generalization gap is the difference between these two. A large gap means your model learned too much from training, even the noise, that's overfitting. If both errors are high, it didn't learn enough, that's underfitting. So, the ultimate goal in machine learning is to minimize both the training and test error, achieving the lowest total error possible. Okay, and now we'll move to the next slide. Means what is model complexity? Okay, model complexity simply means how flexible or detailed your model is when fitting data. Let's make a simple analogy. Imagine drawing a curve through data points on a graph. A model like a straight line is like saying, I'll just draw a rough trend. It doesn't capture small bends or patterns. That's high bias, low variance. A complex a complex model like a 10th degree polynomial draws a very wiggly line that touches every data point. So here what happens means a complex model like a 10th grade polynomial draws a very wiggly line that touches every data point, that's low bias and high variance. So what happens as complexity increases, the model fits training data better, bias goes down, but it starts become sensitive to random noise, variance goes up. That's why as data scientist our goal is to find a perfect balance, the point where the model learns real patterns, not random mistakes. You can think of it like preparing for exams. If you only memorize answers, otherwise you will fail for new questions. That's called overfitting. If you only read summaries, you will miss key points. That's underfitting. But if you understand the concepts deeply, you can answer anything. That's perfect model complexity. So this is what the model complexity. And now we'll move to the next slide, that is example motivation. So let's make all this even clearer with a simple real example. Imagine you are trying to predict the temperature of your city over 24 hours. Okay, if you use a linear regression model, it just draws a straight line. It will miss the morning and evening dips in temperature, that's underfitting. If you use a 10th degree polynomial, it fits every little fluctuation, include the noise from measurements errors, that's overfitting. But a third degree polynomial might capture the overall shape perfectly. Not too smooth, not too rough, just right. That's the ideal generalization. If we plot model complexity like polynomial degree versus error, we get a beautiful U-shaped curve. Training error goes down as complexity increases, but the test error fits first decreases, then increases again. The point where tested is lowest in our sweet spot, the perfect trade-off between bias and variance. This is exactly what we want when building real AI systems, the model that learns patterns, not memorizes noise. So, this is called the example for polynomial regression, and we move to the next slide, that is understanding bias. Alright, now that we have understood the basics, let's focus on one side of the equation, that is bias. So, what is bias in simple words? Bias means errors due to overlay simple assumption in your model. It's like the model is stubborn, it doesn't try hard enough to learn the real patterns in the data. Think of bias like a teacher who always assumes every student learns the same way. No matter what question you ask, the teacher gives the same type of answer. That's high bias. In machine learning terms, high bias happens when your model is too simple, it ignores important relationships in the data and makes similar mistakes across different data sets. Okay? Okay, let look at a real world example. Imagine we want to predict a student marks based on how many hours they study. In reality, this relationship is not perfectly straight. Studying more helps up to a point, but after that it levels up. Now, if we try to fit this data using a straight line like linear regression, our model assumes the relationship is linear. That's an overlay simple assumption. If it will predict too low or high study hours and too high for low study hours. A classic high bias error. So remember, high bias equal to model too simple. Model ignores patterns that lead to underfitting and gives poor performance both on training and testing data. In short, high bias equal to lazy learning. The model isn't trying hard enough to understand the true relationship. So this is what the understanding of bias. Now we'll move to the next slide, that is understanding variance. Okay, variance almost the opposite of bias. It measures how sensitive a model is to small changes in training data. Okay, if bias is being too rigid, variance is being too flexible. It means the model is trying too hard to fit every detail, even the noise. Let's take a simple example. Suppose you are fitting a decision tree to classify animals. If your tree is too deep, it might create only one tiny rule for every single training sample. Like if tail length equal to 3.1 centimeter, it's a cat. Now that might work perfectly on your training data. But what if you test it on new animals? It fails. That's high variance. The model has memorized the training data instead of understanding patterns. Okay. Now you can imagine variance like a student who memorizes entire paragraphs from a textbook. In the exam, if the question changes slightly, they get stuck. So high variance equal to the model changes predictions drastically if the data changes a little. It performs great on training data but poorly on test data. This leads to overfitting. In short, high bias equal to model too simple, high variance equal to model too complex. So now we'll move to the next slide, that is expected error decomposition. So now that we know what bias and variance are, let's put them together mathematically. When we evaluate a model, the total prediction error comes from three main sources, that equal to total error equal to bias square plus variance plus irreducible error. So let's break down this. Bias square means this is the error due to wrong assumptions. Example, assuming a linear relationship when the data is non-linear. Variance. This is the error caused by model instability. If your model gives very different predictions when trained on slightly different data and the variance is high. And the irreducible error. This is the noise or randomness in data that no model can ever remove. Example, sudden weather changes, human mood, or random sensor noise. Now, here is the key idea. We can't do anything about irreducible error. It's just part of real world randomness, but we can control the first two, bias and variance, through good modeling choices. Let's take a real world scenario, predicting house prices. Some differences like rooms of area are learnable. We can model those. But some factors like seller urgency or emotional decisions are random. That's irreducible error. So our goal as ML engineers is to minimize bias square plus variance because that's the part we can control. The simple equation bias square plus variance plus irreducible error explains why no model can ever be 100% accurate. Even the best model have some unavoidable error, and that's perfectly normal. So this is what the expected error decomposition, and now we'll move to the next slide, that is visualizing the trade-off. Now imagine a graph where x-axis represents the model complexity from simple to very complex and the y-axis represents error. Here is what happens: as complexity increases, training error keeps going down because the model fits the training data better. But test error, the performance on unseen data fits, goes down and then goes up again. This gives a U-shaped curve for test error. On the left side of the graph, model are too simple: high bias, high training and test error. This is underfitting. In the middle, both errors are low and close together. This is the perfect spot, the model generalization best here. On the right side, the model is too complex, low training error but high test error. This is overfitting. So for example, degree 1 underfitting the data, degree 3 fits well, degree 10 overfits. As we previously discussed about these degrees in past slides, and now this visual curve helps us pick the perfect model, not too simple and that is not too complex but just right for the data. That's the beauty of bias variance trade-off. And now we'll move to the next slide, that is high bias model behavior. Now let's look more closely at what happens when a model has high bias, also known as the underfitting zone. A high bias model makes strong assumptions about the data. It oversimplifies the learning process. For example, let's say we have a data set where the relationship is actually exponential, maybe predicting population growth, but we choose to model it with a straight line. No matter how long we train or how much data we give, the model will always be wrong. Why? Because it's making the wrong assumption about how the world works. Here is how high bias model behaves. It assumes a very simple relationship between input and output. It shows low accuracy on training data because it doesn't capture real patterns. Both training and test errors remain high and similar. Adding more data doesn't help much because the model itself is too limited. You can imagine like this: trying to describe a movie with only one word. No matter how many times you watch it, one word will never capture the full story, right? So to fix high bias, we need to make the model more flexible, maybe by adding more parameters like increasing model depth or using a more suitable algorithm. That's how we move to the left side of the trade-off curve towards the optimal middle zone. And next, we'll see the finally this part talks about underfitting, one of the most common problems beginners face in machine learning. So, what exactly is underfitting? Underfitting happens when your model is too simple to capture the structure or complexity of your data. Let's imagine a real world example. Suppose you are trying to predict the house prices, but your model only considers one feature, say the number of rooms. You are ignoring other important factors like location, age of the building, or size of the plot because your model is too basic. It can't learn important relationships. The result: both training and test errors are high. In other words, it fails to learn even the training data properly. It doesn't improve much with more data or training. It has bias, high bias and low variance. Here is an easy analogy. Underfitting is like a student who only reads the headings of a textbook before the exam. They don't remember the details, so they can't answer any question, not even from the topics they have seen. To fix underfitting, we need to increase model complexity. For example, use a more complex model like moving from linear regression to polynomial regression. Train for more and add more relevant features. In short, underfitting means your model is too dumb. You need to make it a little bit smarter. Okay, now we'll move to the next slide, that is overfitting. Overfitting happens when your model becomes too smart, so smart that it starts memorizing instead of understanding. When a model overfit, it learns not only the real patterns but also the random noise in the training data. So it performs extremely well on the training data but poorly on new data. Let's imagine another example. Suppose you are training a neural network to classify images of cats and dogs. Your data set is small and the model is very deep. It might memorize every single pixel pattern in your training images. So when you show it a new dog picture, maybe taken in different lighting, it's get confused. That classic overfitting. Here is how we can summarize it. Overfitting equal to low bias, high variance, excellent performance on training data, poor generalization on unseen data. To fix this, we can use regularization techniques, early stopping, or simply make the model smaller or collect more data. So remember this, an overfitted model knows everything about the training data except how to work in the real world, and this is called the overfitting. And now we'll move to the next slide, that is causes of overfitting. So what exactly causes overfitting? There are several reasons and knowing them helps us prevent it early. So let's go through one by one. Too few training samples. If your dataset is very small, your model doesn't have enough examples to learn the general patterns, so it memorizes whatever you give it. Imagine teaching a child to recognize birds by showing only 5 pictures. They'll just remember these pictures instead of understanding the concept of a bird. And next, too many parameters. If your model has too many parameters or layers, it becomes overly flexible. It can overfit anything, even noise. And then noisy data. Sometimes your data itself has noise or mistakes like wrong labels or measurement errors. If your model tries to fit those, it overfits. And then lack of regularization. Regularization helps keep model weights in check. Without it, the model can assign huge importance to small, meaningless features. And then excessive training approaches. If you keep training even after your validation error starts increasing, the model continues to memorize noise. That's last stage overfitting. A simple example, if you train a decision tree and don't limit its depth, it will keep splitting the data until every single point fits perfectly, but it fails on new data. So the key message is too much complexity plus too little data equal to overfitting. So this is overfitting, and now we'll move to the next slide, that is detecting overfitting. The answer lies in comparing training and validation performance. So here is the key signs of overfitting. Validation loss starts increasing while training loss keep decreasing, and there is a large gap between training and validation accuracy. That means not almost same. Learning curves diverge instead of converging. Cross validation results vary widely across folds. The model performs inconsistently on unseen data. So let me give you a example. Suppose you are training a neural network up to 50 approaches. Both training and validation losses decrease. After 50 approaches, the validation loss starts rising, but the training loss keeps going down. That's your signal. Stop training right there. Your model is starting to memorize noise. Ways to fix overfitting include using early stopping, adding L1 L2 regularization or dropout method, increasing training data, or using data augmentation. Okay, And now we'll move to the next slide. Detecting underfitting. Now, just like detecting overfitting, we can also identify underfitting by observing the model performance. Here are the indicators. Both training and validation errors remain high. Model predictions look too simple or generic. Learning curves flatten early at a high error value. Adding more data doesn't help, and the model fails to capture important patterns or relationships. For example, if you train a nonlinear model on a dataset that has a curved pattern, your error will stay high no matter how long you train. That's because the model doesn't have enough flexibility to represent that curved relationship. How to fix it? Use a more complex model like adding layers, parameters, or nonlinear terms. Train for more approaches. Improve your feature engineering like adding new features or interactions. So, if overfitting is like memorizing the book, underfitting is like reading just the cover. In both cases, the model doesn't really learn properly. And next, what are learning curves? Learning curves are one of the best tools to visualize how a model learns over time. They show how the model's error or accuracy changes with training process or data size. The x-axis represents training iterations like epochs or number of training samples. The y-axis represents here error rate or loss. You have two curves, one for training and one for validation error. Learning curves helps us diagnose bias variance issues. For example, if both curves are high, that means underfitting. If there is a large gap between the two, that means overfitting. They also tell us whether more data or more approaches will help improve performance. In short, learning curves are like health checkup reports for your model. So, they show whether your model is learning too little, too much, or just enough. And for next slide, interpreting learning curves, that is underfitting. It is used for underfitting. When a model is underfitting, the learning curves tell a very clear story. Here is what you will see. The characteristics, both training and validation errors are high. The curves converge quickly and remain flat. Even if you train longer, there is no improvement. The model simply can't represent the data pattern. So example, let's say you train a first degree polynomial regression model on the data that's actually curved. No matter how many samples you use, the training and validation errors stay high. That's underfitting. The fix, increase model complexity, maybe use a third degree polynomial or add new features that better capture the pattern. So whenever you see both curves stuck high and flat, you are that's the clue. The model is too simple, it needs to learn more. And this is what interpreting learning curves. And for next slide, so interpreting learning curves overfit. Now your model is overfitting. The learning curves tell a completely different story. Here is what happens. Training error becomes very low. Your model fits training data almost perfectly. Validation error remains high or even starts increasing after some point. There is a big gap between these two curves. This is a classic overfitting signature. Example, suppose you are training an image classifier. Your training accuracy reaches 99%, but validation accuracy stays around 70%. That means the model has memorized training images and failed to generalize. So, fixes for this is adding regularization L1, L2 or dropout and uses data augmentation, reduce model complexity, collect more diverse training. Remember, a healthy model's learning curves should come closer together, not drift apart. So, for next slide, validation curves. While learning curves show performance over time, validation curves show how performance change with specific hyperparameter. For example, x-axis model parameter like tree depth, regularization strength, or polynomial degree. Y-axis means error or accuracy. Here is what usually happens. Training error decreases as model complexity increases. Validation error decreases at first but then increases, again forming the famous U-shaped curve. The point where validation error is lowest represents the optimal parameter value. So example here, if you vary the depth of a decision tree, depth 2 equal to underfits, depth 6 perfect generalization, and for depth 15 overfitting. So validation curves help us tune our models, not too simple, not too complex, but just right. So this is what about validation curves. And now role in model selection. Finally, for this part, let's connect everything together with the role of learning curves and validation curves in model selection. Both these curves are essential tools to choose the best model for your task. Here is how they help. They ensure balanced performance between training and test sets. They help detecting overfitting or underfitting early. They support cross validation to confirm stability. They guide hyperparameter tuning, like choosing the right regularization strength or tree depth. So, most importantly, they encourage you to select models that generalize well, not just ones that perform great on training data. So example, when tuning an SVM, you can vary the C parameter and use a validation curve to find the best part where validation error is the lowest. That's your ideal value. So remember, data gives us knowledge, but curves gives us wisdom. They show you the full story of how your model is learning and performing, and with that, we complete the best model selection. And now, for next slide, why regularize? Now that we clearly understand that what overfitting and underfitting are, it's time to explore one of the most powerful to handle them, regularization. So what regularization is? Regularization is a technique used to prevent overfitting by controlling the complexity of the model. So think of it like putting gentle brakes on your model. When the model starts going too fast, learning too many unnecessary patterns, regularization slows it down just enough to keep it balanced. And if it works by adding a penalty or constraint during training, forcing the model to stay simple while still learning important features. So here is why it's important. It reduces variance without drastically increasing bias. It keeps model weights under control, avoiding large unstable values. It's especially useful for deep neural networks or model with many parameters. It helps improve performance on unseen data. So let's take an example. Suppose you are doing linear regression with 100 features. Without regularization, the model might assign very large weights to random features trying to fit noise. Regularization will limit those weights, helping the model focus on meaningful relationships instead. So, in short, regularization helps your model stays humble and realistic, not overconfident and noisy. So, this is what regularization and types of regularizations we'll see. So for the types of regularization, L1 regularization, that is also known as lasso. This adds a penalty equal to absolute value of the model weights. It promotes sparsity, meaning it can push some weights to exactly 0. This way it can automatically performs feature selection. It decides which features matter and which can be ignored. And L2, that is ridge regression. This adds a penalty equal to the square of the model weights. It doesn't force weights to become 0 but keeps them small and stable. This helps the model avoid overreacting to noisy inputs. And for dropout for neural networks, during training, it randomly turns off some neurons. This prevents the network from becoming too dependent on specific paths, improving generalization and early stopping. Your monitor validation error and stop training when it starts increasing before overfitting kicks in. So, data augmentation, your artificially expand your dataset with transformations like flipping, rotating, or scaling images. This exposes the model to more variations and reduces overfitting. Each of these techniques keeps your model from memorizing and pushes it to actually learn general patterns. So, for next slide, we'll previously discussed about this L1 regularization, that is lasso. So now let's take a closer look at L1. Mathematically, L1 adds a penalty equal to the absolute values of each weight as we discussed, but let's skip the math for now and focus on the intuition. Think of it this way: L1 regularization likes to keep things simple. It pushes unnecessary weights to zero, removing less important features from the model. That's why it's often when we used or when we have a lot of features, we want the model to automatically pick only the most useful ones. So for example, suppose we are predicting house prices with 50 features, things like number of rooms, area, color of the walls, distance, etc. Now, not all these features matter. L1 will automatically reduce the important one, that means weight of unhelpful features like roof color to zero, keeping only important ones like area, location, rooms. This makes the model simpler and easy to interpret, less like to overfit. So remember, L1 equal to feature selection plus simplicity, that equal to better generalization. And if we move to the next part, L2 regularization, that is ridge regression. While L1 sets some weights to 0, L2 strings all weights smoothly. So L2 doesn't want any single feature to dominate the prediction. Instead, it spreads out importance more evenly. It says, don't make any one feature's weight too big, keep all them moderate. Example, let's say we are predicting stock prices and one input features is very noise, like daily Twitter mentions of the company. Without regularization, the model might assign a huge weight to that feature just to fit random spikes. L2 limits this. It reduces extreme weights, leading to smoother and more stable predictions. So, in summary, L1 zero out some weights, feature selection. L2 ridge reduces all weights smoothly, stability and generalization. Both have the same goal: control overfitting and the make model more flexible. And now we'll see the elastic net regression. Sorry, elastic net. So, elastic net uses for both penalties. It mixes L1 and L2 in a single formula controlled by a parameter called alpha. L1 part promotes sparsity, that means it drops useless features, and L2 part keep weights stable and avoids large values. Elastic net is especially useful when you have many correlated features. L1 alone might randomly pick one and ignore the others. L2 spreads weight among them. Elastic net combines both behavior for a balanced result. So example, imagine predicting disease risk using hundreds of gene expression features. Many genes are correlated. L1 might drop some at random, but elastic net keeps them in a balance, improving generalization. So here the takeaway is elastic net equal to balance between L1 feature selection and L2 stability. It's widely used in data science competitions and real world ML pipelines. So for cross validation, one of the most trusted methods to test model performance and ensure generalization. So what is it? So cross validation is a technique that divides your dataset into multiple parts, usually 5 or 10 folds. You train the model on some folds and test it on the remaining one. This process repeats several times so that every fold acts as test set once. Finally, you are average all results to get a reliable estimate of model accuracy. So why do we need this? Because training on one part and testing on another helps understand how the model behaves on unseen data without wasting valuable samples. Example, if you are predicting customer behavior, you can't rely on one random split. It might just be lucky or unlucky. But if you test across all folds using 5-fold cross validation, you'll get a stable, trustworthy result. So it detects overfitting early, provides a fair evaluation, helps compare multiple models, and guides hyperparameter tuning. So in short, cross validation equal to a safety test for your model's real world performance. And early stopping. So now let's to look at another simple yet powerful technique, that is early stopping. In deep learning, we often train models for many approaches. At first, both training and validation errors goes down, but after a point, the model starts overfitting. So, validation error rises even as training error drops. Early stopping solves this by monitoring validation loss during training. When the validation loss starts increasing when you stop the training right there, even if training loss keeps decreasing. So, example, you train a neural network for image classification. After 30 approaches, validation loss starts rising. That's your signal. Stop training. You have reached the best point of generalization. So, benefits: save computational time, prevents memorization of noise, improves test performance. You can think of early stopping like cooking pasta. If you boil too little, it's hard. If you boil too long, it becomes mushy. So, early stopping means you stop it just the right time. And dropout regularization, one of the most famous regularization techniques used in neural networks. Dropout works by randomly turning off some neurons using training. Why would we do that? Because if every neuron always depends on others, they become lazy, right? So they memorize together instead of learning independently. By turning off random neurons temporarily, we force the network to learn multiple pathways to reach the right answers. So you can imagine it like teamwork. If one player sits out, other learn to handle the game themselves. So, for example, in a CNN, that means convolutional neural network for handwritten digit recognition, dropout ensures the network doesn't rely on few neurons to detect certain strokes or curves. Instead, it learns general patterns that work for all digits. So, dropout usually uses a rate like 0.2 or 0.5, meaning 20 to 50% of neurons are randomly dropped per iteration. So, the result is better generalization, reduced overfitting, a more robust model, and data augmentation. So, data augmentation is a beautiful trick to make your model smarter without collecting new data. So, data augmentation means artificially expanding your dataset by applying transformations to existing samples. So, the common techniques are image rotation, flipping, cropping, scaling, and adding noise, and audio, pitch shift, time stretch, all these, and text, synonym replacement, and word shuffling. So, this model is to make the model see more variety so that it learns general features, not just specific patterns. So, example, if you are training a model to classify cat or dog images, if you rotate or flip them, the model learns that is a cat is still a cat even when you viewed upside down or sideways. Benefits are reduced overfitting, improves robustness, and works greater with small data sets. So, if you can't collect more data, just be creative, augment it. Your model will thank you later. So, this is what data augmentation. And finally, for the selection, let's talk about ensemble methods. One of the most smartest ways to reduce both variance and bias. An ensemble method combines multiple models to make predictions, kind of like taking the average opinion of many experts instead of trusting just one. So there are two major types: bagging like random forest and boosting like XGBoost. Okay, bagging means trains multiple models independently on different subsets of data, so then combines their predictions, usually by averaging or voting. So this reduces variance and make predictions more stable. And boosting like XGBoost trains model sequentially even more model focuses on mistakes of the previous one. This reduces bias and variance, improves overall accuracy. So, real world example, when you search something on Google, hundreds of smaller modules vote or contribute to the final ranking. That's an assemble power in action. So, benefits of ensembles is more stable and reliable results, better accuracy, less prone to overfitting than a single complex model. In short, one model can make mistakes, but many models together make wisdom. And visualizing overfitting. When a model is overfitting, it tries to so hard to fit every single training point that it even fits the noise. The random fluctuations that doesn't matter. If you visualize it, the model predictions like line will look like a twisting snake passing through very single data point, even the outliers. That's overfitting. It memorizes, not learns. And imagine a student who memorizes every single example in the book, even the printing mistakes. When a question appears in the exam, they get confused because it's slightly different. That's exactly what happens with an overfitted model. The graph shows extremely low training error, high test error, a U shaped validation curve, error goes down, then up again. So this is what the graph showing. And example, let's say you are predicting student marks with 10th grade polynomial. It overfits all training points perfectly but fails completely on new students. Okay, and visualizing underfitting. Here is the model is too simple to capture the real pattern of the data. In a graph, you will see a straight or overly smooth line that misses the curves or trends. Both training and test errors are high. Think of underfitting as a student who didn't study enough. They only knows the basics, so they can't handle detailed questions. For example, if you use a straight line model, linear regression to predict a curved pattern like temperature changes throughout a day, you will get a large errors both on training and test data. So visually the line doesn't pass close to the data points. It looks too simple. The model is blind to important relationships. And ideal model visualization. Now the $1,000,000 question is, what does a perfect model look like? An ideal model sits right in between underfitting and overfitting in the golden middle zone. Usually it's smooth curve that follows the overall trend, but the data ignores random noise. It doesn't chase every small bump or dip. Instead, it focuses on the main pattern. In this case, training and validation errors are low and close together. Predictions are stable and generalized, well to unseen data. Think of it like being a balanced student. You study enough to understand the concept, but don't waste time memorizing everything word. That's the real learning. Example, in a noisy dataset of house prices, a third degree polynomial fits the real trend without reacting to random price fluctuations. And trade-off summary graph. Here is the final big picture, the bias variance trade-off graph that summarizes how everyone connects and everything connects. X-axis model complexity, how flexible the model is. Y-axis error, both training and validation. When we increase model complexity, Training error decreases because the model fits data better. Validation error fits decreases, then increases again, forming that U-shaped curve. At the left end, high bias, low variance underfitting. At the right end, low bias, high variance overfitting. In the middle, best balance, ideal model. Example in polynomial regression, degree 1 high error underfit, degree 3 perfect trade-off, degree 10 fits noise overfit. So this is what trade-off summary graph. And example polynomial regression. We'll take a simple data set where y follows a quadratic function with a bit of random noise. Now watch what happens. Low degree polynomial means degree 1 draws a straight line missing the curves, and that is overfitting. High degree polynomial degree 10 draws a crazy wiggly line through every point, that is overfitting. Moderate degree 3 smooth curve that fits the trend but ignores noise, the ideal model. This one simple example demonstrates the bias variance trade-off visually. Low degree high bias, high degree high variance, moderate degree balance. So this is what the example for generalization and quantifying bias variance. Alright, how we actually measure bias and variance in practice. Here is the simple approach. Train your model on multiple different subsets of your dataset and then observe like how it behaves. If the mean error across these subsets is high, that means high bias, the model consistently gets things wrong. If the variance of errors is high, that means high variance, the model predictions change too much across different samples. So example, imagine predicting house prices with small random subsets of data. Your model always predicts around the same wrong value. It has high bias. If your model gives very different predictions each time, it has high variance. This analysis helps diagnose whether you need to add more features or complexity to fix bias, or simplify or regularize the model to fix variance. So bias variance quantification, like a doctor's diagnosis, it tells you exactly what wrongs your weather model's learning behavior. And empirical detection. Another way to detect bias and variance is through empirical testing. This means repeatedly training your model on training random subsets of data and checking how predictions vary. If predictions change drastically each time, high variance. If predictions are similar but consistently wrong, high bias. You can visualize this with errors bars or scatter plots. Wide errors means high variance, consistently offset results mean high bias. Example, let's say we are using a decision tree for classification. If small changes in the training data cause the tree to look completely different, it's suffering from high variance. If the tree structures look almost the same every time but performs poorly, it's high bias. So empirical detection helps you adjust your model practically, not just theoretically. So now let's connect these ideas to real world machine learning tasks. Like you'll find bias and various issues everywhere, like spam detection. An overfitted model memorizes specific SAM words like free or offer and fails when spammers use new ones. And stock prediction prices. Two flexible models fit random market noise, that means high variance. And face recognition. If the model performs well only on training photos but poorly on new angles or lighting, that's overfitting. Handwritten recognition, too simple, a model misses letter variation, that is underfitting. Medical diagnosis, small datasets can easily lead to overfitting. The model works on training patients but fails on new ones. So, yes, understanding bias variance isn't just theory, it's the secret behind every successful AI model deployed in the real world. And relation to training dataset, another key factor, In general, small datasets are high variance, overfitting risk increases. Large datasets, variance reduces, better generalization. That's why collecting diverse, high quality data is just as important as choosing the right algorithm. For example, predicting house prices with just 50 examples, you will probably overfit. But with 5000 diverse examples, your model learns general patterns instead of noise. And remember, regularization techniques works even better when combined with larger, richer data. And bias variance, model types. So, type of ML model has its own bias variance personality. Let's look at a few examples. That is linear models, which has high bias, low variance. They are simple. They are simple and may underfit complex data. So decision trees, low bias, high variance, very flexible but can't overfit easily. Random forest, multiple trees averaged together, they balance bias and variance nicely. Neural networks can have low bias but high variance, need careful regularization, support vector machines. Their bias variance behavior depends on the kernel and parameters chosen. So, choosing a model type is not just about accuracy, it's about managing this trade off intelligently. So, the key takeaways are, alright, let's summarize everything we have learned today. Our key takeaways from the bias variance trade off and overfitting means bias, that means error from overlay symbol assumptions, causes underfitting. Variance, error from model sensitivity, causes overfitting. Goal, minimizes both bias and variance for the lowest total error. And trade off means reducing the one, usually increasing the other. Find the balance. And techniques to control variance is regularization, cross validation, early stopping, data augmentation, and ensemble methods. Example recap: linear regression on complex data, high bias; deep decision tree on small data, high variance; moderately complex model, best generalization. So, for the conclusion slide, let's quickly recap what we have achieved today. We learned what bias and variance means, and we explored underfitting and overfitting, their causes and effects, and we studied techniques like regularization, dropout, and early stopping, and we visualized how ideal models balance both perfectly. Remember, understanding the bias variance trade off is like understanding the heart of machine learning. Every algorithm, from linear regression to deep learning, lies within this balance. I hope you found this session insightful and easy to follow. If you did, give this video a thumbs up, share it with your friends, and subscribe to Gudsky Research Foundation for more ML tutorials. In next video, my teammate from Gudsky team will continue this journey, diving deeper into model evaluation techniques and regularization case studies. Till then, keep exploring, keep experimenting, and keep believing in your potential. Thank you.